Hello and welcome to a drive-by code session. In this episode, we're going to build a parser. This time, we're gonna go more towards doing computation. So, the parser for this time is gonna parse a simple arithmetic expression that can basically do add, subtract, multiply, and divide. So, an example of that would be 1 plus 2, 1 plus 2 times 3, and so forth. So just starting off simple. But the calculator that we're going to build will actually be able to evaluate the answer based on this expression and give you the correct answer. In this case, the answer should be 7, if I'm doing that correctly. So let's get started. So first thing we're gonna do, again, Whitekit did this code. I'm just gonna replay what he did and explain it. So the first thing is we're gonna generate a new package JSON file, and again install Nearley.js. If you're not familiar with Nearly at all, go back to the previous videos that we created in this series, and you will be able to get a good introduction to it, I hope. Okay, so now we're gonna make a grammar for this, and we're gonna sort of repeat what we already done in past episodes, which is a small grammar to match numbers. So we're gonna say a number is a number of digits followed by a dot followed by some more digits, or simply a bunch of digits. What's digit? A digit is either one digit or a digit followed by more digits. And again, this is called the recursion trick that allows us to match one or more of something, in this case digits. And then what's a digit? A digit is a character within the range 0 to 9, and this guy is called a character class, and we've also covered that in past episodes. So now with this, we're gonna sort of take the matched strings and sort of build up an AST or a representation of what was matched. In this case, ID says just take whatever data is there that is there. In this case, it is going to be some one character long strings here for digit. ID means just return whatever is there. It's customary that when the right hand side of a production rule has only one single symbol in it, as is the case here and here, we're just going to use the ID function to return whatever the first thing is. But in the case where it has more than one symbol, we need to write a more detailed transformer. And this guy, so these functions, actually this one as well, we call these transformer functions. That's what I call them. I don't know if there's a better name for these things. But this guy is gonna say, I got two strings, one coming from the digit symbol, one coming from the digit symbol. I'm just gonna join them together to comprise the thing that I want this guy to represent. We will write transformers for these two rules as well. Number going to digits and number going to digits, a dot and a digit. For a number going to digits, we're gonna take the match from the first symbol, that's data at 0, and use the number conversion function to convert it to a number. For the decimal number, we will kind of use string concatenation to form the correct decimal number based on the input, and then again use the number conversion function to give you an actual JavaScript number. So with that, we need to set up the Nearly compiler. That's C stands for compiler. We'll set up the Nearly compiler to compile this math.ne grammar file to a JavaScript file. We'll set up a script to do that so we can run that conveniently on the command line using npm run gen parser. And now we have a math.js, which is the JavaScript representation of this grammar. And now we can start writing a parse.js that utilizes this math.js to parse some values. First, let's just feed a number in it because that's what we have, what we're able to parse at this point. Okay, so we'll need to require the math.js that was generated by the Nearly compiler and then plug it into this instantiation of the Nearly parser. Once you have a parser instance, you can still start feeding strings in it, and we're gonna feed in 1 into it. And it gets us 1, and you can see by the fact that, let me run it. I'll run it. Okay, by the fact this is an array that has a number of 1 in it, by the fact that it's not in double quotes or anything like that, we know that it has converted it into a number. Okay, and it can do decimal numbers as well. Okay, that's good. So next thing we want to do after that is to be able to do sums. How do you match a sum? Well, a sum is a number, a plus sign, and then another number. At least that's the simplest formulation of a sum. Let's have some optional white space. We did an episode on white space, so we're going to use that trick here to match 0 or more white spaces, which are either spaces or tabs. And we'll inject the optional white space, sort of sprinkle them into the places where we allow optional white spaces. And so now we can have a sum, and we'll say the input can either be a sum or just a single number. And let's also write a transformer for this. We could choose to generate an AST, which is represented by a JavaScript object. And I'll show you how that works. So this is an object with a type property, which says sum. And then left hand side and right hand side, both of which are represented. Oh, this needs to be 4. So the left hand side would be 1, 2, 3, 4. So the left hand side is going to be this number, which comes from the 0th index, and then the right hand side is going to be this number, which comes the 4th index. And so if we ran the parser, let's see, if we gave it a sum like 1 plus 2 and we ran the parser, compiled the parser, now run it, we get this object, which is an AST, abstract syntax tree node, which represents this particular sum. What we could choose to do, though, instead of representing this this parse as an AST, we'll talk about ASTs in the future, so I'm gonna do that. So I'm gonna skip over ASTs for now, and instead we're gonna evaluate the sum right away by taking the number here and the number here and just using JavaScript to add them together. And if we did that, regenerate the parser, run it, we actually get the sum. And this is very interesting. This is like the parser is doing the evaluation of the result immediately, and that is something that's an option that you have. Now we're able to have sums, but that's not good enough. If we wanted to have a more than one sum and then sum that sum with another thing, so 2 additions in a row, this grammar is at the present not able to do that, and we'll see why it complains. It's saying I see like another white space here, but I'm not really expecting that because it is still trying to match a number, trying to match the decimal point or trying to match another digit here, and that is because the grammar doesn't allow sort of compound operations. It only allows a number, plus sign, and then a number. So if you want more computations to happen, what you're gonna have to do is, again, use a recursive trick. So what is this recursive trick here? Well, you can say a sum is a number, a plus sign, and then another sum, which then could have even more plus signs in it. And and because of the power of recursion, you can actually do it endlessly. You can have endless number of addition symbols. But you have to stop somewhere. So we also need to allow a sum to simply be one number. And so let's see this work. Let's see if this even works. So recompile the parser, regenerate the parser, and run this. And we're seeing this is clearly wrong. Just jammed 1, 2, and 3 together. It's probably because we don't have a transformer for this rule, so we'll add it. Just use the ID transformer. And now it actually does evaluate the sum for us. And I'm gonna actually try. I just said you could add any number of these. So I'm actually gonna try going all the way up to 9, see if that works. Yeah, that seems to be right. I did that all in my head. Okay, so, all right, switch back to the replay terminal. Okay, so now we can extend that and say, well, and we don't even need this, we don't need this rule even to say that the input could either be a sum or a number, because a sum can already simply be a single number. So we actually don't need this rule here and end up with a simpler grammar. And that still works. All right, what about multiplication? If we want to generalize to multiplication, subtraction, and division, let's extract out this plus sign as an operator and allow the operator be one of these 4 symbols. And we're going to use the special symbols for multiplication and division because we want to look cool. And we'll, instead of calling this sum, we'll call it operation now. And now we'll use a switch statement to differentiate between the 4 different operations based on the operator symbol. The word sum, we need to fix this renaming, the residue of our renaming, and call that operation instead of sum. So now we regenerate the parser there and parse, and now it can still do its job. It can do additions, etc. But it can also do multiplications. So this is 2 times 2 is 4. Try a few more things. Oh, division should be look like that. 2 divided by 5 is 0.4. So the different operators are working now. Okay. Only that there's a problem. Operator precedence. So at the moment, our grammar doesn't handle doesn't sort of favor multiplication over addition, which it actually needs to do. So given this guy, at the moment, what the grammar does is, so it doesn't matter at the moment which of these orders it is. The grammar is actually gonna compute the last one of those first, and then compute the compound one. And the reason that is because of the order of this rule. It's saying an operation, let's say this guy is an operation. It's saying the operation is first a number, which that is a number, and then an operator, that's the operator, and then an operation. So this is another operation, which recurse back to itself, and then this guy matches another number here, number, and then another operator in this case, and then this is still another operation, but then it uses the next rule down here that says, oh, this is a number, well, it was a number first before it was an operation. So this could be a number here. So because of this, the ordering of this rule, we'll end up with a tree that looks like, oh, this is super messy, I'm sorry. Let me do it again. We'll end up with a tree that basically looks like this. So this is a operation, and then this is the next, the sort of compound operation. So this inner operation is the one to the right, whereas what we want is the inner operation to favor the multiplication over the addition. And in order to do that, we actually have to rewrite the rules. I'm gonna call the sort of differentiate between the additive and the multiplicative. We'll say the multiplicative, it can either be multiply or divide, because in a sense a division is kind of just a multiplication with a reciprocal. And then we'll say additive is either the plus operation or the minus operation, and we'll have the additive sort of defer to the multiplicative. So basically we're saying an additive thing is gonna add together a bunch of multiplicative things. So if we have this and this is gonna be multiplicative. They're gonna get matched with a multiplicative first. And then the additive will actually combine these two guys together like this. So having this guy start off first and start at the top level and then defer to the multiplicative will allow this to happen. But of course, we'll also say a multiplicative could also potentially just be a number. Like it could just be a 5. And that's what allows for the case of just 5 plus 7, for example, because a single number can be interpreted or derive a multiplicative. So that's the strategy. Let's make it happen. So we'll say additive is a multiplicative, plus or minus sign, and then more additive. That's to keep the recursion going, to have another additive after it. Or it could just be a single multiplicative. And then a multiplicative is a number, multiply or divide sign, and then another multiplicative, and that's the recursion rule. Or multiplicative can be simply a number. So we basically just, instead of this one general operation, we have two operations, one of which sort of has a precedence over the other. And then we'll write the transformers for it, adding in the white space as well. So at this point, we have some mistakes here, which he will fix. So this is still a switch statement, but only handling the plus and subtract cases, and this one only handling the multiply and divide cases. And we start the grammar out at additive, and then an additive can be an addition of a bunch of multiplicatives, and this is the thing that makes it work. And the multiplicative is multiplication of a bunch of numbers. You can look at it like that. So so now at this point, let's test it. I'm gonna write some code to test it myself. So let's see, what's the answer here? This is 2 times 2 should happen first, and then add 2, so that should give us 6. If we did it the other way around, it should give us the same answer. Yes, but if you did it the wrong order, then it would have been 8. So this seems to work. I'll just do a couple more tests here. 2 divided by 2. So this should have done 2 divided by 2 versus 1. And then add that to the result of 2 times 2. This should give us 5. Yes. Okay, so this parser seems to work. And we've done a simple example of operator precedence. And this is how you would do it with a context-free grammar here. If you have any questions about this, if this was confusing to you, please write me in a YouTube comment. The next steps for this grammar is to allow for parentheses, but as well as adding functions to the mix, and also variables, adding variables to the mix. So that's coming up in the future. Hope to see you soon.